Hello everyone, I am Masud Rahman from Purdue University. I'll be discussing our work, Bootstrap Advantage Estimation for Policy Optimization in Reinforcement Learning. In standard reinforcement learning framework, an agent interacts with the environment at discrete time step, and the environment transitions to the next state and it produces a reward. The goal of the agent is to learn a policy which maximizes the expected cumulative reward. And after training, given an observation, the agent outputs the best possible action. An important assumption of RL framework is that the tasks follow an MDP, which is a Markov decision process. That means the agent acts on a state representation where a state consists of all the necessary information to take an optimal action. This assumption allows to design effective RL policy as history of the state information does not matter and only the current state information is enough. However, in practice, though it is reasonable to assume the underlying system or the task follow an MDP, the observed state might contain partial information which complicates the learning process. Moreover, the reward still depends on the true state S. Our observation of the MDP might be different, and due to the incomplete view of the true MDP state, the actual state might contain confounding information, noise, and also the state space might be too big to explore efficiently, and overall the task that the MDP is complex and that will make the policy learning challenging. In this paper, we propose to mitigate these issues by incorporating data augmentation in advantage estimation, which is an important component of the objective of, in the policy optimization. Now I'll discuss the evaluation protocol. We can think of two broader categories of evaluation: the sample efficiency, which is a measure of how quickly the agent learns, and often measured in environment time step. This is a measure during the training of the policy. On the other hand, the generalization is a measure of how good the agent performs in unseen scenarios, which is evaluated during test time. So these test environments typically consist of scenarios which differs from the trained data. Thus, this is a challenging metric which measures whether the agent truly learned the task or it simply memorizes the training. For a particular example, here we can see ProgGen star pilot environment. For the training, a limited variation of the environment are given, and for the testing, it is tested on some unknown variabilities. So we can see that if no precaution are taken, then the agent might easily overfit to the limited variation of the environment during training and eventually fails to generalize to even in slight change in the environment. In this paper, we address this issue using a method based on data augmentation. Our solution is based on the policy gradient method, which aims to directly optimize the cumulative reward directly. We implemented our approach with PPO based objective here. This can be viewed as the approximation of the policy gradient loss, such as natural policy gradient, and TRPO. Policy gradient implementation details in this case consist of training individual components of the algorithm, such as learning value function, policy function, and advantage estimation. In this PPO objective on the right, we can see that the ratio here is consists of the probability of an action given a state, and on the top part is the probability from the current parameterization of the policy, which is theta, and the denominator consists of the old parameterization of the policy. So thus this ratio is important to control the update of the parameter, and it is important that we compute this ratio correctly. And the A of t, which is the advantage estimation, intuitively we can say that this estimate determines the advantage of an action from current policy compared to the previous old policy. And what is data augmentation in this context? So we can see the data augmentation as the transformation on the observation, and the assumption is that it will keep the semantic of the observation the same semantic in terms of the reward structure of the environment. However, it allows to be the context to be different. So in this case, the context is usually defined to be the unnecessary information relevant to reward. So this can be, for example, a background color for an environment. So typically in image-based observation, we can apply different image manipulations such as random cropping, rotation, cutout color, that we can assume that it will keep the semantics same. And I would like to highlight that it's not only the image-based observation that the data augmentation can be applied. It can be also applied on different vector-based state representation as well. So, and it has been observed that the approach is useful for high-dimensional scenarios. In this paper, we used both approach for our evaluation. So the issue with the naive data augmentation is that in the ratio computation, so usually in the top part of the ratio, the probability is computed using the data augmented version of the observation, while the old policy is computed on the non-augmented version. And this creates a mismatch between this ratio computation, which makes it theoretically not sound. So in this paper, we still want to use the data augmentation. We would like to explore how we can incorporate them in a more sound way. So as data augmentation has many benefits, which helps to learn a better policy in terms of sample efficiency and generalization that has been observed in the current literature, and would like to use the data augmentation in this case to compute the advantage estimation instead of the ratio, and the ratio is still computed on the non-augmented version of the data. And that's the novelty of our method, and I will briefly describe the methodology here. So the idea is to compute the advantage estimation for different data augmented version of the observation. That means if we have m different data augmentation method, we'll compute m different version of this advantage at each time step at, and we'll also consider the original non-augmented version of the data. That's why on the average in the middle equation we can see that there's m plus 1 for the average computation. And finally, once we have the advantage for each time step, we followed the approach in the generalized advantage estimation paper to compute the final Bootstrap advantage estimation. So here is a complete practical algorithm that can be implemented to solve a task using our method. So the main difference compared to the standard PPO is the use of data augmentation in line 10 through 12. First, the data augmentation is applied to create different varieties, and then those variety of data augmentation is used to compute the BAE estimation, and finally it is used to compute the loss. To verify the effectiveness of our method, we conducted experiments on both image-based and vector-based observation, which is from ProgGen and ProgGen deep mind control and PyBullet environment. In this case, the ProgGen benchmark is allow the procedural generation, which allows to test generalization performance of the agent. As of the and also the ProgGen environment consists of discrete action, and the robotic environment like DeepMind control and PyBullet, so they consist of continuous action. So we covered both discrete and continuous scenarios as well. As of the baseline, we compare with the standard PPO algorithm, and then the naive or pure data augmentation method RAD, and also we compare with another data augmentation approach DRAG, which aims to correct the issue with regularizing the policy and value network. The ProgGen environment consists of image-based observation, and the robotic control environments consist of vector-based observation. So first, we can see that in terms of the value loss and the policy loss, on the left, we can see on the red our method perform better, much less loss in terms of value and the policy, which shows that the use of data augmentation in the advantage estimation is helping to learn better policy and the value estimate. And this translates to the performance in the sample efficiency and the generalization performance. On the right top, we can see that our method performed better compared to the baseline standard PPO DRAG and the RAD. We observe similar performance where our method performed slightly better compared to the standard PPO and the DRAG. Interestingly, we can see that on the top right, the RAD, which is on the orange, performed badly compared to the standard PPO as well. And we observed similar trend in robotic control tasks, so in this case DeepMind control. So for the quadruple run environment, our method performed better, and we can see that the DRAG and the RAD, which is on the green and orange, actually perform worse compared to the base GIE PPO, so that's the standard one, which is on the blue. And on the cart-pull 3 poles, which is a variation of the classic cart-pull environment, it's a cart-pull, but it has 3 different poles, so the more the state space and the action space, so they are much higher. And we observed that our method performs slightly better compared to the standard PPO, while the RAD performed badly, which is on the orange. And we observed that for the PyBullet environment, these 2 environments, our method performs comparably with the standard PPO, while the DRAG and most prominently the RAD, which is the pure data augmentation based approach, actually worsen the performance. So we consider this as an important feature of our method, that in our experimented environment, if our method cannot improve upon the existing performance, the performance is still remain the same. However, for the RAD, the performance tends to degrade a lot, and which is not surprising given the theoretical nature of how we compute the ratio that we discussed in the previous few slides back. So in summary, we in this work, we propose a Bootstrap advantage estimation, which apply data augmentation to compute the advantage estimation for the policy gradient based method. And we observed that empirically in several environments consist of discrete and continuous action, image and vector based observation space. In different scenarios, our method empirically shows better performance compared with the baseline tested. And here is we open source our source code in this link. Feel free to explore and let us know if you have any comments or suggestions. I'd be happy to answer any question. Thank you for your attention, and I'll be happy to take any question. Please feel free to reach out to me.